So, hello and welcome to session 188 in the AI Safety Reading Group. Tonight we'll be discussing the blog post, Formal Metaethics and Metasemantics for AI Alignment. This is work done by Jun Ku, who has a graduate degree in philosophy from the top-ranked Metaethics program. I think that's probably a unique program, a unique university, but I haven't actually looked up which one that is. She describes herself as a computational meta-ethicist, and I looked up that there is in fact only one person in the entire world who describes themselves like that. So we have a blog post on Medium, which is actually a description of a software program that is available on GitHub and also on Metaethical.ai. And this is in particular, even though I mostly ask people to read this blog post, I will be talking almost exclusively about the actual program. The program was published in October, and in January of this year, a large amount of, well, you could almost call them comments, a description was added. This probably has helped quite a bit from my understanding, at least. But before I dive into this, I need to make some disclaimers. I'm quite outside of my field here. I don't know much about metaethics. I don't know how I can figure out what claims are good or bad. I don't know how to make sense of metasemantics. The most glaring example would probably be the tagline for Metaethical.ai, which is AI that does what we should want it to do. And when I look at the code and the description, it seems to me like this is what we would ideally want the AI to do, not what that we should want it to do. But June has published a paper on norm descriptivism, and I think the answer to this is actually in that paper. But I haven't read that paper, and I'm not sure I would even be able to read that paper. So take what I say with a big grain of salt. Further, I haven't read the entire description. It's around 5,000 words. I haven't made any attempts to download or run the actual code. And still, I'm going to be so bold as to make some criticism here and there. And this is kind of a nitpicking, a lot of it. And I think I need to state up front that I think this is really great work. But I'll still come with criticism where I see it. So let's start. What is Metaethical.ai? It is a fully technical, ethical goal function for an AI. Goal function and utility function and probably reward function is mostly the same thing in this context. So the important thing here is that this is something that can be executed. The code is written and it bottoms out in the sense that the individual parts of the code, there are tests and you can run it, and it's something that will actually compute an answer. But it seems like in the tests, there are only parts of it that are being tested. So that I couldn't find an example of an end-to-end test. Like you can imagine a world with like two people, one of them wants chocolate and the other one wants strawberry, and then try to figure out how to satisfy their preferences and this kind of thing. I couldn't see whether that was done. I think it would be possible, but there might be a part of it that is not possible. There are some rather strong assumptions. Unlimited compute and a complete causal model of the world and of all the human brains in the world. So those are really strong assumption. Unlimited compute means that you can try every solution and see which one is best, at least those that are not infinitely long. So that's a kind of super intelligence, you could say. So the way this is summed up by Jun Ku is this is not a ladder to be thrown away, but a scaffold that is to be superseded. This is implemented in not set L, which is a programming language emphasizing sets from the 60s, but set LX, which is a more modern implementation running on the Java virtual machine, which is this is the logo for it. So if you know anything about mathematical work on infinities, you'll know that this is probably not something that is meant to run fast. But Metaethical.ai is a set theoretically view of AI, and for that reason, having a language that is good for sets and not good at anything else, basically, does to some extent make sense. However, I think very close to nobody uses ZLX, so it is really niche. And when she posted it to the general AI safety community, I think the choice of language harmed her ability to communicate quite a bit. I mean, many other languages like Python has great support for sets, but Python just does many more things, and Python is something that a lot of people who work in AI knows. So for me, actually, personally, I work in Prolog. So for me, looking at it, ZLX was like totally trivial. So for me, that wasn't a problem at all. Now, as for the coding values or goals, June describes them as optimizing for solving the problem rather than communicating the solution. And when I look at it, I think actually what she's optimizing for is optimizing for correctness. Things like having tests and trying to make the code structured in a way that makes errors stand out. And even though it pains me to say this as a software developer, correctness might just not be the right choice here, because I think optimizing for readability is much more important. You can see this, for instance, in that the code is very terse. The variable names are very small, and in particular, there is a word. There's an explanation in words, and there's a code, and they have different structures. And I think this is a real problem. And in a moment, I'll try to show the code and see how it relates to the explanations. And when you see me do this, you'll sometimes see me jump around a bit and say, we'll get back to this later, and please ignore this for now, and things like that. And I think this is something that makes it much harder to understand. And on the technical side, from the code from the website, I can't copy paste it into this presentation here. So everything is done using images. But those are, of course, minor things. Let's go and see the description in words. What is Metaethical AI? We have a mathematical model of the world and the brains, and then the utility function is constructed by having a social welfare function to the set of extensional rational utility functions of the brains. And this is one of the things I noticed here was they're saying the adult human brains, and as the way I see the idealization procedure, it seems to work for just all human brains, and I think everyone is a nicer shelling point than just the adults, because then who gets to decide precisely who are adults, etc. Anyway, this one here can be split up into 4 parts. First is that the world is given as a Markov model, and this arrow triangle here means that this can be expanded, and it can be expanded a lot. And this over here refers to is a link to the actual code. Then the utility function for the brain is it depends on the brain's decision algorithms if it made more optimal decisions. And then we, in order to compare brains, then we need to cache them out as in terms of to cache the brains terms out into terms of the real world. And then finally, when we need to merge these, we choose a center of gravity among these extensional rational utility functions. So this is like the basic overall structure. Now let's have a look at the code. So here are the line numbers in the left, and you can see here the Metaethical AI utility function is a procedure that as input takes the world and a set of brains, and then it returns a utility function down here. So this is the code that you can actually look up on Metaethical.ai. So the first thing we have here is the world model. So in this world model, we get the set of all states that the world can be in. This is section 1.1. And then we define a utility function. So we have the entire world with all its possible states. And then for each possible state, we make a ranking of them. And then we just say a utility function is a mapping from the states to this ranking, basically. So it's a ranking of all states that the world can possibly be in. In order to calculate that, we need to, given the brains that is given as input, then we need to find their decision algorithms. This is section 1.21. And once we have these decision algorithms, then for the brains we need to find the rational utility function cashed out again in terms of references for the to the world. Then we have the set of the utility functions for the brains. Then here we do something that's not explained, and I think I kind of understand it, but I can't really explain it. So we'll jump past this and go down here where we have a set of possible utility functions. Recall that up here we have the set of all possible utility functions, and then here we can compare them by saying which one is closer to the utility functions that the brains have. And once we have a comparison of this, then we can just sort all the possible utility functions and then take the best one. That's the code down here. And once we have the best utility function, it'll be returned, and that is the main overview of what metaethical AI utility function actually does. So you can see here there are a number of subfields that we need to dive into, and let's start with 1.1, where we have the world as a Markov model. So this is, again, you can see with this arrow I've folded out the entire description of the world as a Markov model. And it's a reasonably detailed specification. There's 250 lines of code. There's also some tests, and this is a reasonably standard Markov model, following also a rather standard textbook. So I think this is perfectly fine. You should note that it assumes it's a Markov world, meaning that nothing acausal can ever happen. And of course, in AI safety, if you go to less wrong, you will find a lot of things about acausal bargaining, etc. So, but I think that this is a very fair assumption for now. So let's go to part 1.2. You are given a brain, and then you need to figure out what decision algorithm does it actually use. So there is again some description of this, how this is done. So let's see how Jung say you do this. Here is the description, and the description follows on the next page, and 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 on the next page. So I really can't do this justice, right? I can't go through all of the implications here. So what I can instead do is to dive into the code, and we try to find some of the things that I think are most relevant, and I can show you a representative sample of the code. So we have some brains, and we need to find out what decision algorithm is implemented by this brain. So we start by finding the set of all possible decision algorithms. There's some testing code here that needs to be ignored, and how to find all the decision algorithms in the world is something we'll get to on the next slide. But once you have all the decision algorithms, then you need to filter this set down with the ones that correspond precisely to this brain, the ones that, and of those, it also needs to have the lowest complexity. We're talking about something like Kolmogorov complexity. And then among those algorithms, we take the one that is the better explanation, and then we return that. So there's of course a trade-off between whether it's precisely corresponds to the brain, the Kolmogorov complexity, and this better explanation, and there needs to be some kind of trade-off between these values. Better explanation is actually also cashed out into 4 different things that the decision algorithms should be as good as possible in. We'll get to this in 2 slides. But first, let's see what is the set of all decision algorithms. Here, you can see what we do is we have a brain, and then we look at how many states can it be in. And let's say the brain can be in 1 million states. Then we take all decision algorithms with complexity less than 1 billion. And then this is the actual code that does this. I think this is an implementation of first order logic, but I'm not 100% sure. I think I would probably have preferred to have an implementation with referring to Turing machines, because that's generally the way I think about the set of all algorithms. But let's go to the question of when is a decision algorithm a better explanation for what the brain actually does. And the way this is implemented is that first we calculate for all explanations a sort order, requiring we give each explanation a score, and this score is calculated with 4 parts: how ambitious the decision algorithm is, minus how complex it is, minus how much instrumental irrationality there is, minus the incoherence. So these are again 4 things that are defined for these algorithms. I won't go into all of them. In the explanation, this was called charity. And to me, the word charity doesn't really map to this. Incoherence and instrumental irrationality is not that close to charity in my opinion. Okay, let's go on to how we actually, once we have the values of the brains, how do we refer this to the world? So first, we need to figure out what are the values of the brain according to its own representation. We'll get to that in the next slide. But once we have this, then we need to go to the world and then find the expressions, figure out what they refer to, and then try to see how we can, for all the world states that can, the states that the world can be in, what utility do we assign to it? And this is basically how we do this. And then we sum up the utilities. I don't think I'll go into more details here, but let's instead have a look at how to figure out the utility of the brain according to its own representations. So again, we have a rational utility function, a procedure that given the world and the brain. It starts by looking up all possible social choice utility functions, which is basically everything that the world that the brain can refer to, and the rankings. They are not defined in states of the worlds, but in something a bit different. I'll get to that in a moment. But one thing you might be wondering here is, why is there a social choice here in the brain? Because there is not that much social inside a single brain. So here you can see precisely where the domains and the range are for these inside the brain utility functions, and there's some more bookkeeping, I would almost call it here. And then finally, what we see here is that these possible utility functions are then weighted against each other with a voting weight, and this voting weight is in fact Bostrom's parliamentary model for how to manage moral uncertainty. And this is an implementation of this. I think it's slightly clumsy, perhaps, maybe because of limitation in ZLX. But this is basically Bostrom's, and I think Toby Ord was also part of creating this parliamentary model back 15 years ago or something. Okay, so we have the world model, and we have the brains, how they work, and in order to compare them, we have cashed it out into things that relate to the real world. Now, this was the last part. This was the original utility function, and then you remember there was this merging here, where we find the difference between them. So this is a repeat of what I've said previously. And then what we do here is that we find the difference in ordinals between the utility function and the utility functions, and then we square it to ensure that it's non-negative. And the problem here, the way I see it, is that someone could be a utility monster. So if we imagine that everybody has, reasonable utility functions about, and the world should be, rather normal, middle of the road, and there's one person who really favors that he should be given all the power, then this distance will be very large for him towards all states where he doesn't have ultimate power. And in this case, of course, just squaring it will make it very large. So the center of gravity algorithm will tend to give Bob very much power in this situation. So when I looked at this, and again, I was unable to look through it all in detail, so some of this might actually be covered. But I didn't find any discussion of how to make this faster, right? With other these kind of theoretical algorithms like EXTENSIONAL, for instance, we do have approximations and we have some path towards some kind of feasibility. Also, like an optimal Bayesian reasoner can be approximated to some extent, but there's no discussion of this. There's a problem of mind crime, and that this, as far as I can tell, implements every possible mind crime. There is also no possibility for moral growth. The agential identity part seems to imply that you basically end up with this idealized decision algorithm and these values, and then you can never have anything else. And I think this, on a conceptual level, has a lot of similarities with EXTENSIONAL, and I think some kind of explicit comparison with EXTENSIONAL would be nice to have. There's also a very similar suggestion for how to for what an AI should do in an ethical sense, called coherent extrapolated volition by Eliezer Yudkowsky. I would also like to see some comparison here. Stuart Armstrong has made an impossibility theorem about how to distinguish values from limited rationality, and I would also like to see some kind of relationship between the existing work and Junque's work. Of course, social choice theory have a number of other impossibility theorem, most famously Arrow's theorem, which is also not considered. But in total, I was very impressed with this. There surely has been a lot of work, and I hope this is something that will be a scaffold to be superseded. That is all for today. Thank you, and see you next week.